Welcome to the special edition of the Uptime Wind Energy Podcast. I'm your host, Alan Hall. And if you have been following the news lately, there are several ongoing campaigns by blade manufacturers to deal with wrinkles in their blades. Even though these wrinkles are minute in appearance, these fabric deformities can create weaknesses that reduce blade life. And as we have seen all over the news, these wrinkles are also expensive to remove and repair. Our guest is Morten Handberg, Chief Blade Specialist and partner at Wind Power Lab, which is a blade consulting company located in Copenhagen, Denmark. And if you haven't heard Morten on our podcast previously, Morten is our resident blade whisperer. In our episode today, we'll be discussing how wrinkles are created, how they produce stresses, and why they are difficult to eliminate during manufacturing. Morten, welcome to the program.
Hi, Alan. It's nice to be back again.
If we can catch up a little bit, you and I talked to each other about blade wrinkles several weeks ago now, and that topic has just gotten progressively hotter and hotter and hotter. So I thought now's the time to get it out there about what's happening with wrinkles and why we should care. Now, and at the same time, you sent me some pictures, which just scared the heck out of me because I thought these wrinkles were relatively small coming from an aerospace background. Wrinkles don't tend to be big in aerospace products, but the wrinkles you showed me are large. And I'm trying to understand, like, what is the real threat here? Let's just start there. What's the real threat if a wrinkle is in the side of a blade? What does it matter?
So it really matters depending on the location of the wrinkle. So is it in the structural spar cap or in a heavily load part of the blade, let's say the root or the transition zone? Then even small wrinkles can actually turn into very large cracks. And it doesn't really matter what the size is. It's more if it's in an area that allows it to grow into a crack. Because as soon as it does that, it will just continue growing at a pace defined by the loading conditions. It can ultimately turn to a blade failure. Obviously, the larger and more aggressive the cracking, the wrinkle is, meaning how steep the angles are of the wrinkle. So if this is the shape, it matters if the wrinkle is shaped like this or like this. Then how much stress it requires for it to develop, because it's all about how much reduction that it creates to the underlying blade structure. If you have changes in the UD laminate and it starts to fold, it means that the strength of the UD laminate is reduced. And then it's just about a matter of time before it then turns into a structural crack.
And the defect doesn't just apply to the plies where the wrinkle is. It puts additional stress on the plies that are around it. Is that the loading problem?
Yeah, because I mean, if you remove the loading capacity of one area, it has to be taken up by another, right? I mean, the loading doesn't go away. So if you have a wrinkle that starts to turn into a crack, it means that all the UD fibers, they're essentially removed from the equation. They're not taking up any blade loads anymore. And that then creates more stress to the boundaries of the crack, but it also creates more and more stress to the other laminate areas of the blade, because now they have to take over whatever part this area of the blade, but this area of the laminate was taken over. And this is also why some of these cracks can turn to blade failures, because at a certain point, then the amount of laminate that's been removed does not allow for the rest of the blade to carry the load anymore, and then it eventually fails.
What does this look like as the wrinkle progresses into a larger defect? Is it a delamination that happens? Is it a physical crack? Like you start breaking plies? What does it look like?
If you have a wrinkle, as I said, it's kind of like a fold inside the laminate. And if that fold is creating a wave like this, then on the top of the ridge, you're consistently, the wrinkle is trying to stretch itself out during operation. And that creates a lot of stress on the top part of the ridge, and that's where you create a crack. But on the lower side, where you have the slopes, they are trying to lift. They're lifting themselves out of the laminate, essentially. That's what's going on. And that then means that it debonds from the laminate. So what we typically see is that on the lower boundaries of the wrinkle, we create delamination, and then on the ridge, we create a crack in the direction of the wrinkle.
Wow. Okay. So depending on where you're looking, you may see a delam or you may see a crack on either side of it. But you probably have both?
If you have in a very sensitive area where you have very high loading, maybe one or the other is more, then maybe the crack is more aggressive than the wrinkles, so the crack will progress faster than the delamination develops. If you're in a lower loaded zone, then maybe it's the delamination that is the most prominent one developing. So you can't really say whenever you see a wrinkle or you see a wrinkle in development that it will be the crack that will be the denominating, or it will be the delamination. I mean, if you're in the spar cap laminate, then you would cut away the laminate layers before the delamination becomes anything significant, and then the crack will be the meso failure.
So the blade manufacturers today, when if they have blades out in service and they realize that they may have wrinkles, is it easy to detect? If you're on a turbine, if this blade is on a turbine, can they find wrinkles simply, or is there a way to do that, or does this get really complicated for them to identify where the wrinkles are?
What is normally done when the blade is produced is that after it's been demolded, either the shell or the full blade, depending on the manufacturer, a QC technician will go through the entirety of the blade on the outside and on the inside and look for waviness or rises in the laminate to see are there any wrinkles here, and then get those fixed if they're outside of factory specification.
How are they identifying those? Is it an ultrasound? Is it a flashlight? Is it a tap test? What's involved there?
A tap test wouldn't make any sense because it's still solid laminate, so there's no deep bonding that you could detect from a tap test. You can use ultrasonic or NDT. You typically do that for the load carrying part of the blade, for the spar caps. Not all OEMs are doing that. And that is a problem because often some of the wrinkles that we see leading to major structural damages or blade failures is because the quality checks at factory were not sufficient or not carried out in a way that would allow for them. But skilled quality technicians, they would be able to see them either visually, just by looking at it, by knowing how does a healthy laminate look from a laminate with a distortion. You can also, to some extent, use you use a light dispersion test by holding over a flashlight over an area and see how the light passes through it. If there's any major changes to laminate structure, that will show in that way. But it requires some skill to detect it that way. So again, it's not something that you would send out any guy on the street and he would be able to find it. You need to know what to look for at the factory. The best way to do it is to use NDT, but that's typically only applied to the main load-carrying parts of the blade, because that's what you're mainly concerned about. But wrinkles can happen anywhere. It's not something we can say it always at 6 meters. It's only on the leading edge. It's only in the spar caps. They can occur anywhere where you have a laminate stack.
And then, so in the factory, easier to identify because the blade's sitting there and you have probably the proper tools. Once you're in service, though, what happens? Is it only ultrasonic?
I mean, for the inner third of the blade, you can still walk in, do a manual inspection to check if there's any changes to the if there's any visible changes in the laminate structure. Not saying a damage yet, just by seeing if there's a certain rise in the blade suddenly without any need for it. That typically indicates that there's a wrinkle in this area. They can either be longitudinal, they can be transverse. Typically longitudinal, they don't matter as much because they're in line with the UD fibers. So the UD fibers are still unidirectional. So it's really rare that we see longitudinal cracks, wrinkles develop into damages just on their own accord. Transverse wrinkles, they do tend to develop into cracks, even the smaller sizes, because they change the structure.
Is that because of the compression and tension cycles the blade goes through every rotation, that it's just putting an immense amount of stress on that one weakness?
You're putting stress on that the laminate's not designed for. It's not designed for the UD laminate to be bended. And you can have transverse wrinkles that doesn't develop into cracks if they're far enough out in the blade, but you are rolling the dice a little bit because just because it didn't develop in 2 years doesn't mean that it won't happen ever. You're just hoping that it doesn't develop over the lifetime. So we've seen wrinkles develop after 10, 12, 15 years of operation. And, everyone was saying, well, this doesn't matter. This blade is past, in the warranty. So it would have developed if it ever was. But that's just not how it works because it's fatigue is a threshold. So the blade is designed for, let's say, most blades are designed for 25 years. Then they're designed for a nominal load or nominal load cycle over that 25 years of lifetime. But if you have a wrinkle that weakens the blade in that structure, it means that you're reducing that threshold. How much is, that requires very advanced simulations, but at the end of the day, it is a reduction. So a wrinkle should always be considered as something that will cause a potential damage down the line. Doesn't matter if it's 5, 10, 15, 20, or 30 meters from the root, maybe even 50 for, a 70-meter blade. It's something that we can't say exactly how fast or how slow it will develop or at what point in time. We can just say that, well, it is a weakness, and we know that these wrinkles, they can turn into cracks eventually.
Okay, I want to walk back into the factory for a minute. What is creating these wrinkles? Is it the mere fact that there's so many layers of glass and that they're manually applied and you got people kind of stepping on them as they put these plies down? Or is it the fact that we're making bigger and bigger blades with the same number of people, so there's just a little bit of a rush? What's driving the wrinkle issue today?
Wrinkles have always been there. It's not a new invention. It's been there as long as we've been building things out of composites. We've had wrinkles because it's just a change in the geometry of the laminate. That's all it is. So it's not something new. It can also happen if you stretch the laminate. You change the uniform structure. You can also create waviness in that way. It's not wrinkles as we think about them right now, but it's still a change in the structure that can affect the blade negatively. But the way that they occur can actually have several causes. So one is quite commonly that when you're laying up the glass fibers, then as you lay down these long glass fiber mats next to each other, then sometimes there's a need just to adjust them a little bit or move them around, and that can then create some small folds. And then as you're applying more and more glass fiber, if you're not aware, then you can build up a larger and larger waves that then can create this wrinkle. So it's just by pushing the fiber mats around, even slightly, can have really big consequences. Another cause is the core material that are used in the blade to add thickness, but without adding a lot of weight. These also comes in large sheets that are moved around and adjusted. But if there's a large gap between two sections of core material, that creates a separation where there's no resin, there's no fiber, and then when the blade is cast, then the fibers can actually get stuck down into this core gap and then create a wrinkle in that way. And it can also be from adding core material adjusters where you change the thickness of the core material in a small area that also creates these waves in the structure. So there are just really several paths to the same effect, but it is whenever you are creating sort of the space underneath the laminate where you then get a resin-rich area, then it gets locked into this wrinkle. And it's something that it doesn't happen after in operation. They're not created after manufacturing. It's created during manufacturing, and then it's locked in, and then will develop over time during that period of time.
That's interesting. So listening to some of the discussion as an electrical person, seeing some of the news articles and hearing some of the difficulties that some of the OEMs are having to eliminate wrinkles, is it ultimately a design to build question that maybe the way that the blade was designed is encouraging wrinkles? Is that the way to think of it? Because it's roughly the same manufacturing people doing the same job over and over again.
My view on it is that the wrinkle problem has been persisted for decades in the blades, but the blades are becoming more sensitive because they're becoming longer. They are getting more optimized. So you use the materials in a different way where you have less buffer in your blade to account for deviations inside your blade. So that also means that any manufacturing defect is much more sensitive because you don't have the same conservatism when designing your blades anymore. It's not because your manufacturing method is changed. Not as I see it, because that's still essentially the same way. but the focus on quality assurance have not gone up with producing longer and more optimized blades. And it should be this. The more you optimize it, the more focus you should have on the quality assurance, because you become more sensitive to structural damage. And that's also why we're seeing the fatigue damages we're seeing in the field today, and that a lot of owners are experiencing, is because that the blades were not thoroughly checked at factory. And if the OEM is saying otherwise, then you can just look at the defect that's there, and it shouldn't be there. You shouldn't expect to have critical damages or blade failures after 1, 2, 3, or 5 years in operation. It shouldn't happen. And that means that defects were overlooked that should have been detected and repaired at factory.
Does that indicate a need to upgrade or to maybe change the way we're inspecting blades during the manufacturing process, like during the ply layup and plus after the fact, once the blade has been cast?
It's a good question. I think that obviously there are ways you could. I'm sure there's ways that you could optimize your manufacturing, but a good place to start is to increase your focus on quality control. And that's where you need to start. And then maybe you can implement changes to the manufacturing over time that would reduce your the frequency of these defects occurring. But right now, with the methods that we're using for manufacturing, then we need an added focus for quality control. And number one is to do NDT, especially of the structural critical areas. I would say all the blades should be checked, because we know that wrinkles can appear anywhere. But we need to start with that point, that it shouldn't be possible to produce a 80, 90, 100 meter blade without doing an NDT inspection, and then send the blade out in operation, then hope for the best.
So because the margins are lower, the blades get longer, right? So we learned from our previous designs, we're making them lighter to allow them to be shipped, and a lot of other reasons, cost reduction, right? Less weight is less material, which is less cost. That then forces, so an improved quality system and maybe even a training system to how we're going to build these blades. That seems like a big effort. And when watching some of the OEMs go through this cycle, it seems like it's taking a long time to rectify the situation, months and months and months. Does that make sense? Why it's taking so long is because they're changing so much of the internal systems?
But the focus has been for a long time on building bigger and longer blades faster, and releasing new methods into production and into the field, because you had to stay ahead of the curve with the other manufacturers. And that has taken over some of the focus from quality assurance of the blades. That has been down prioritized in order to optimize cost and get the blades longer. Another factor in it is also that we're introducing carbon more and more inside the blades, and glass fiber is a really nice material when it comes to some manufacturing defects, because it has a lot of elasticity. So it means that it can work with the manufacturing defect for a longer period of time. Carbon fiber doesn't work like that. If you have any change to the carbon fiber, because it's a lot more brittle, it develops into a fatigue damage much faster. So you see a rapid development in the damages for carbon fiber blades than you would for traditional glass fiber blades.
So carbon's less forgiving, and we're seeing more carbon as the blades get longer, and that it sounds like some of the carbon pultrusions are coming from a sub-supplier into the system. Does that make sense? That at least in some of the discussions I've seen, it seems like it's a supplier issue, but it's a composite supplier issue, which to me says carbon fiber. And if carbon fiber is less forgiving, you're bringing in something that may not have been inspected to the level maybe it should have been, and then it gets stuck in a blade and it just magnifies the issue. Is that kind of where this is headed?
I mean, that might be a way to look at it. But I mean, if the OEM is putting together the blade, it shouldn't really matter if they're producing the pultrusion or they have a third party. They should be responsible for making sure that the pultrusion is checked and that it's inspected, and making sure that there's no manufacturing defects in that before installing it inside the blade.
Does it become more critical on the carbon fiber to do an ultrasonic inspection because it's such a critical load path for the blade?
I mean, it would develop faster compared to a glass fiber, but for a protrusion, if you're talking about glass fiber, it's equally necessary. The severity, you could say, is almost the same, but the how do you say, it will develop faster for the speed of development is faster. And the reduction in strength is also greater with carbon because you're relying much more on on the load capacity in carbon compared to glass fiber. So it would take longer for the damage to develop. But again, the ultimate consequence would be the same as long as we're talking about the spar caps, if it's glass fiber or carbon fiber.
That would help explain some of the early failures that they think the industry is seeing is maybe it's in the carbon. That would make a lot of sense from a mechanical standpoint, right? Because, you're right. You're using carbon to cut the weight out, and because it's a stronger fiber, if there's a problem in the carbon, look out. It's going to show up pretty fast.
The only safe way to check it is through NDT, because if the wrinkle is small enough, it wouldn't show up in a visual check, and so it's the only safe way to do it.
What does a repair look like to fix a wrinkle in a carbon spar cap, let's say, or a fiberglass shell? What are we talking about here? Are we talking about days, weeks, months to fix some of these things, particularly where it's a highly loaded area?
If we're talking about the spar cap, we're talking about weeks or months if the blade is repairable at all, because you need to remove so many layers and you have so many iterations of buildup to restore the blade that, in a lot of cases, it would be deemed a replacement blade. Most damages, they can be repaired, assuming that they have not developed into a large crack that has affected the majority of a shell. Then most damages, most wrinkles, they can be repaired if they're outside of the spar cap area. I would say if they haven't developed, I would even go so far to say I would assume all of them.
And then if now once those blades get out in service and say if they've missed the quality inspection and you have this wrinkle, depending on where it is, what are you as an OEM? Are the OEMs reaching out to those customers to say, hey, this blade mold, this blade factory had this issue, we need to track this? Is that what's happening in industry right now? Is just a follow-up happening to say, hey, be aware of this? Or is it more aggressive, like we need to stop turbines?
We have seen a lot of cases where if the OEM recognizes that they have if they have an issue on multiple blades within the same batch, that they reach out to the owners with this particular blade type, and then stop turbines if they see that this blade serial has high likelihood of issues. Then they would stop that, or they would say, okay, inspect, keep it running, but we'll inspect within a short time frame. So we have seen cases like that where the OEMs have taken a proactive approach because they recognized after the fact that they had a large issue with their blades. But I would say, as an owner, if you see a blade where you recognize that this is an issue with wrinkles, I would recommend that if the OEM haven't taken any action and they don't seem like they're going to, that then you have to take action, because otherwise the problem can escalate and require a lot of downtime, a lot of replacements, and a lot of repairs if you're not proactive on your own. If it's something it's something where it's suspected to be in the spar cap laminates, we would recommend doing an NDT inspection. If it's something that looks like it's in the shell laminates, externally, an internal inspection can be a really good place to start, just to see, are there any visible signs of blade defects.
And then from the insurance side, and insurance has become more and more of a factor in the operation of a wind farm. Are the insurance companies starting to step in a little bit and force the operators to go look and to be proactive about this?
We've seen them ask questions to owners, whether they have taken any steps, but it hasn't gone so far that they are pending the insurance renewal on them doing inspections for it. But But again, if this is a problem that will persist, then that could be a likely outcome that, if you haven't done your own check of your own blades, then that would be that could affect the policy.
All right, Morten, this issue is still in its infancy. I think there's a lot more coming up about blade wrinkles worldwide. Obviously, there's a lot of concern by operators. If they have a blade that has wrinkles or they're starting to experience some failures, they should probably be reaching out to Wind Power Lab. How do they do that?
You can reach us on windpowerlab.com or reach out to us via LinkedIn, or you can also find me on LinkedIn and reach out to me directly.
And we'll pull all the contact information in the show notes so you can get a hold of Morten directly and to Wind Power Lab, because blade wrinkles have really grown into a massive issue, and it's time to put some resources to stop them. And Morten, this has been so great to have you back on the podcast. We love having you on. Everybody, our blade whisperer, Morten Handberg, thank you for being on the podcast.
Thanks for having me.